That math research flourishes most in situations where you got a very healthy combination of different people with different backgrounds but similar interests. Topology is an important subfield of mathematics, and what attracted me to Notre Dame 30 years ago was the fact that there was a really strong group in topology. Mark Behrens joined us from MIT. He's a specialist in stable homotopy theory. He is interested in a cohomology theory that's called topological modular form theory, which is very much related to my interest in physics.
But when I came here, I first met the topology group here and was really blown away by the tradition of excellence in topology. I could see the possibility of building what would be truly a topology group that would be of national importance. And that really excited me. I've got 3 projects that I'm really engaged in right now. One project has to do with developing a new tool for studying the homotopy groups of spheres. The tool that I'm trying to develop is TMF-based atom spectral sequence. And the hope is that this tool will allow us to go into higher dimensions. This work with my collaborative team on the TMF atom spectral sequence has unexpectedly led us to think about a major problem in the field, and that's called the telescope conjecture. We have a definite counter-conjecture. The question is whether these 2 kinds of homotopy groups are the same or are different. The current evidence out there seems to say that one of the kinds of homotopy groups is computable and the other one is incomputable. What our work seems to be showing is no, this other kind of homotopy group also could be computable. It just may be different, but we may be able to quantify the difference. One thing that really got me energized when I first came to Notre Dame was a collaboration of people here at Notre Dame and at the University of Chicago. One of the biggest unsolved problems in the homotopy groups of spheres has to do with a problem in dimension 126. And so if we can push our computations up there, it gives a real chance of saying new and interesting things. Now, this collaboration began as a computational collaboration, but then we got involved in thinking about the telescope conjecture. So we got to work on this, and the computations started to flow, and they started to say interesting things. This project developed here in the Midwest is something that's going to bring us together, I think, for years to come.
Pavel Neff joined us in 2016. His advisor was a famous physicist, Fadeev. Then he moved more into a mathematical direction. It's great to have somebody who grew up in physics, whom you can ask all these questions, but he understands what you're saying since he also speaks mathematics.
In Notre Dame is unique in that it is something unheard of to be gathering a group of researchers working on between topology and quantum field theory, and for me this is precisely the sweet spot where I fit in. My work is, in the big picture, is trying to provide the theory for the path integral. So that the path integral is supposed to have some nice properties with respect to gluing and cutting of the underlying manifold. And sort of one big program is reconciling these two approaches and sort of casting this Feynman diagram approach in a way that it is automatically compatible with gluing and cutting. The other one is replacing the manifolds on which we are considering path integrals by something else. Instead of manifolds, you are considering something combinatorial. It turns out that in some special cases you can replace the manifold in the path integral by this picture. And there is certain interesting coherences that one should observe, so that sort of combinatorial reconstructions of this picture should be compatible with this path integral. I think that one thing I would really like to do is to extend the construction of perturbative path integral compatible with gluing and cutting to gluing and cutting with corners. It uses the machinery of higher categories to describe these gluings and cuttings. And this is one interesting direction to go. The machinery of understanding the path integral is universal, and it is to be applied to physically relevant examples of path integral. But in particular, these modern developments in condensed matter physics, these topological insulators, that is very close to the project that I'm pursuing with my collaborators, which is about the interaction of field theory in the bulk and the field theory on the boundary of a manifold. So I am anticipating applications there.
Schommer-Pries came from the Max Planck Institute. He is an expert in topological field theories and category theories and uses that to express physics.
My research focuses on the interaction of 3 areas: topology and quantum field theory and higher category theory. I work in the interaction of these three areas. My work has been related to the classification of these topological field theories, understanding the entire moduli space of all possible topological field theories of some kind. But recently, we've been able to make many advances in the classification of topological field theories. When we classify these TFTs, what we often find out is that they are classified in terms of familiar algebraic structure. So with extended field theories, when we start cutting up in different dimensions, we also see interesting algebraic structures emerge. This correspondence allows you to translate topological arguments and constructions into the world. The classification results from my work, also from the work of Jacob Lory on the cobordism hypothesis, these are relatively new. I think is really exciting at this stage is that we're getting these new classification results, and that allows us to really export techniques from topology to other areas. Notre Dame has been really strong in topology, and the Midwest in general has been one of the strong centers for topology in North America. I haven't seen that anywhere else where there's a directed effort to create a powerful group. And that is what really drew me to Notre Dame.
Andy Putman joined us from Rice. He is a specialist in the moduli space of algebraic curves. So it's related to algebraic geometry, it's related to differential geometry, it's even related to string theory.
The Midwest is one of the most exciting places for topology in the world. I feel connected to the broader community of mathematics and to a tradition. I really like to study what are called moduli spaces. When you're trying to study just one geometric object, it's really fruitful to study different ways you can deform it and change it into other things. And so moduli spaces encode the ways that you can deform geometric objects. What I'm really excited about right now is the study of what's called the unstable cohomology of the moduli space of Riemann surfaces. We know that there is vastly more of them than there are of the stable cohomology. They're sort of like dark matter. We know it's there, but we can't see it, and we have no idea what any of it looks like. I wrote a paper with Neil Fullerton titled The High-Dimensional Cohomology of the Moduli Space of Curves with Level Structure. And so what I find exciting about this paper is really a question in algebraic geometry. We answer it using topology, but if you look at our proof, we start off doing sort of geometric and algebraic topology, and we reduce it to a very difficult question in representation theory. Then we do work in representation theory for a while, and then we reduce that to questions in algebraic combinatorics. It really exemplifies the unity of mathematics. I find mathematics most exciting when it's sort of 2 or 3 areas coming together at once to solve a problem.
What we're doing here at Notre Dame is definitely different than what you'll see across the country. I think that we are building a great group, and we're still not done.
The department has certainly made a lot of big strides in terms of attracting outstanding people. Their presence gives us so much more to ferment on. New ideas, new backgrounds.
Because we cover such a broad range of topology here, I think there's an opportunity to acquire a breadth. Because we all talk together and we all come to the same seminar, you'll be exposed to an enormous range of topics.
The strength of the group here in topology is that it's coherent whole. What graduate students bring to the table is they bring their youthful excitement about this and that, and they come up with their own ideas. They stimulate you. I think of it as investing in the future of mathematics.
Like there's been a really strong sense of support coming both from the department but also from the university. That's very refreshing.
All of the faculty members genuinely respect each other. There seems to be an atmosphere of collaboration, an atmosphere of working together to solve problems. I think this is really a unique feature of our department, something that makes it a real pleasure in terms of a place to work. I think it's a great place to do research, a great way to learn.